Hello, everyone. My name is Aditi. I'm a senior product manager for Amazon FSx. I'm joined by Manish Talreja, who's the principal product manager for Amazon S3, and Mark Roper, who's the principal engineer for Amazon FSx. Mark will join Manish and I for Q&A after the talk. All right. So all three of us have spent years working directly with customers running high-performance workloads. And pushing the boundaries of what's possible with storage. We are going to share a little bit about what we've learned about high-performance storage for AI, ML, analytics, and HPC workloads. We are going to walk through some real customer use cases, real-world examples, dive into technical capabilities that enable performance at scale, and introduce exciting new features along the way. Let's start with a fundamental question. Who needs high-performance storage? And the answer is a lot of different workloads across a wide range of industries. So think about machine learning teams running large language training models on massive data sets, data analysts querying petabytes of data interactively. Or think about researchers running weather simulations or drug discovery with tens and thousands of cores. And the list goes on. But what ties all of these together are two things. First, that these are compute-intensive workloads. So they require hundreds and thousands of cores, CPU or GPU resources. And second, they're all data-intensive. They depend on fast, reliable access to massive scale of data. And that second part, that's where things really get interesting. Let me show you how. So we frequently hear from our customers that they love that with AWS, they can spin up compute clusters, run their workload faster than ever before, and then spin them down once their workload's done, and stop paying for those resources. This is the magic of the cloud. So ideally, you want this. You want, as you add more compute, more CPU, more GPU resources, you get proportionally more work done. Ideal, linear scaling, beautiful. Here's the problem, though. What if you have a storage solution that cannot keep up with the performance requirements of your workload? And in that case, the work done or your throughput plateaus. And you can keep throwing CPU, GPU resources, but the performance will not scale linearly with it. And the reason being that all those compute instances are now competing for access to the same data store. And that data storage has now become the bottleneck. This is specifically painful because we see that 90 to 95% of spend on these workloads is compute. So when your compute is sitting underutilized, waiting for data, your time to run gets shorter and your cost goes up. So in an ideal world, when you're architecting your solution, you would want your storage to scale linearly with your compute so that it never ends up becoming a bottleneck. Before diving right into solutions of what we've built at AWS to address that very bottleneck, I want to acknowledge that customers come to AWS from two different paths. On the one hand, we have the customers that are running HPC, ML, AI workloads on premises for years. Their workloads are based on file-based access, and they want to maintain that paradigm and move to the cloud, gaining the benefits of the cloud. And on the second hand, we have the customers who started in the cloud from day one. So that means that they have their data stored in Amazon S3, and their applications are built around S3 APIs. So just with a show of hands, who here is using file-based applications today? Oh, awesome. And who here is using Amazon S3 as their data lake? That's pretty good. That's a great mix of customers. And this is also very accurate representation of what we see with our customers in production today. So we're going to cover each one of these, but let me start with lift and shift file system customers. So the question remains, why do file system remains the preferred choice for so many of these high performance workloads? Couple reasons, but the primary one being familiar interface. So researchers, data scientists, and developers know how to work with files and directories. It's just more intuitive. The second is POSIX permissions. So when I say POSIX permissions, file systems give you granular access. When you have multiple users accessing the same data, you want to give control. You want to make sure that you're controlling who gets access to those files, who can write and execute those files. And the third is consistent data access. Again, if all of your users are accessing the same file system, you want to make sure that the data that they're reading is consistent. The consistency is guaranteed. There are no stale reads, and that is where file system is used. Back in 2018, we found that many customers wanted all of these benefits of file system along with the ease of use and scalability of the cloud. And that is when we launched FSx for Lustre. FSx for Lustre is built on the open source Lustre file system. So any of you who've heard Lustre before? Okay, that's pretty good. So Lustre is the open source high-performance file system. It is one of the most popular high-performance file systems. It is used by national labs across the world. It is used by ML, AI, and HPC applications on premises as well. So it goes from applications range from training and inference all the way to weather modeling and genomic analysis. And so what we've done is Lustre is really powerful, but it's also notoriously complex to manage. What we've done is basically taken all the benefits of the fast and scalable Lustre file system and combined it with the management and ease of use of a cloud solution. So we've offered a fully managed, fully elastic, and fast FSx for Lustre file system. Let me walk you through all of these one by one, starting with fully managed. So what does fully managed means? Fully managed means that this file system is tested and operated at an unprecedented scale. We're also consistently monitoring all the hardware resources that are underpinning the file system. So assume that one of your server runs into a hardware failure. And in that case, we automatically monitor it, automatically detect it, and replace the server with a healthy server to keep your file system healthy at all times. We've also done the heavy lifting of ensuring that your file system is built on the latest and greatest technologies at AWS and the latest and greatest technologies offered by the open source Lustre community, and make those available to you with full API support. All right. Now I want to talk about elasticity. We've made Lustre fully elastic for the first time in the cloud. We were hearing growing pains from the customers as they were scaling their workloads in the cloud. Growing pains such as data does not grow linearly. So for instance, if you have ML training runs, you generate terabytes of checkpoints, and then you clean them up. Your simulation spikes, and then you wrap those projects. So your data requirements are always going up and down. And there's this constant battle that you never want to run out of storage, but at the same time, you don't want to pay for unused capacity, right? That's one thing. And the second thing is that not all your data is active data. You're not actively using all of that data to be stored on the SSD file system. So you need it for your hot data, but you still need your terabyte, your checkpoints, and your results stored, but not on the fast SSD. Because if it is stored on your faster SSD tier, it gets real expensive real fast. So think as you're scaling your data set to petabyte scale. As you go to petabyte scale, it gets really hard to just operationally manage, and the economies don't scale either. That is why we launched FSx Intelligent Tiering earlier this year. So with FSx Intelligent Tiering, we offer virtually unlimited storage capacity, which means that the storage capacity grows and shrinks automatically based on your usage. You don't have to worry about it. You'd never run out of storage, and you never have to pay for storage capacity that you're not using. Second point is intelligent tiering between storage tiers. So we keep all your active data on your fast SSD and automatically tier your less accessed data to the colder, low-cost tiers. And we manage all of this. You don't have to worry about it. We do it intelligently based on your access patterns. And finally, the economics of it are quite compelling too. For the colder, as an example, for the colder tier, you pay ½ cent per gigabyte per month. And to put this in perspective, your overall solution comes down to be 34% more price performant compared to your HDD solutions on premises. Now let's talk about speed. These are the performance levels we are delivering in production today. FSx for Lustre is the fastest storage for GPUs in the cloud, and it delivers the lowest latencies in the cloud. This performance metrics are what keeps your compute fully utilized. Let me walk you through how FSx for Lustre delivers this performance so that you can customize your file system based on your workload requirements. Each of the dimensions shown here, you can play with them independently, and that's one of the ways you can even make it even further price performant. So here's a simplified view. On your left, you've got your compute instance that's running your workload, and on the right, you've got your storage, you've got your file system. File system has two kinds of servers. It has the metadata server, and it has the storage server. So your metadata server is basically handling all your metadata requests. Think about creating files, listing directories, managing permissions. Your metadata server takes care of all of that. And then we have the object server. Object server is what handles your actual data reads and writes to and from the file system. Both of these servers are backed by storage disks. And when you talk to storage, your compute instance basically talks to this metadata server and storage server over the network. Now I'm going to show you how each of these components comes into play when we talk about performance and how you can change those based on your workload requirements. Let's start with throughput. So when you're using multiple client instances, you're running thousands of training processes, simulation jobs. They're all accessing the same file system simultaneously. This means that you need more throughput. And by throughput, I mean how many bytes per second you can read or write to the file system. So to deliver this throughput, FSx for Lustre file system basically scales out with multiple storage servers working in parallel to serve your requests. This parallel distribution across hundreds of storage servers is how we deliver over 1 terabytes per second of aggregate throughput. So when all of your compute instances are talking to the file system, your requests are going to not one, but multiple servers in parallel, and you're getting the power of those multiple servers every time, and that's how you get over 1 terabyte per second of aggregate throughput. This enables fast parallel data access to hundreds and thousands of cores. All right. Now, most high-performance workloads are heavy on throughput and relatively light on metadata. But recently, we started noticing that customers were using FSx for Lustre for more metadata-intensive workloads. So you can think about home directories, user research workstations, and interactive applications where you're constantly listing directories, opening files, checking permissions. So last year, we launched a capability to scale out your metadata servers very similar to your storage servers. Again, your metadata servers can be scaled out independent of your storage servers and your storage capacity. What this helps with is you get 15x higher metadata IOPS when compared to before when you could not scale out. And we are further doubling down and making sure that you don't run into metadata bottlenecks. Recently, we made an update to the Lustre software, which enables 5x higher directory listing performance. Now I walked you through aggregate throughput. I walked you through metadata IOPS of the file system as a whole. Now I want to talk about what happens with a single compute instance interacting with the file system. why am I even talking about a single compute instance? So we have seen that EC2 instances on Amazon and across the board compute instances have really improved when it comes to their network bandwidth. We've gone from 25 gigabits to 100 to now 3200 gigabit per second with P5 instances. And all of this performance is great, but it's not amazing when you cannot leverage it when talking to storage. So when you're looking at a traditional file system, your traditional file system generally talks to your compute instances over TCP network, and it only interacts with one NIC on the compute instance, which was true for FSx for Lustre as well for 2 years back. You're only interacting with one NIC, and because of that, your throughput gets limited to 100 gigabits per second. And that means you're leaving so much throughput on the table. So what we did was we launched EFA, EFA support. EFA is Elastic Fabric Adapter, which is built on Amazon's SRD protocol. What it helps you do is it helps you communicate with the compute instance across multiple NICs, and it bypasses the operating system layer completely. And how that is helpful is now you're not using a lot of your CPU cores in figuring out which NIC to communicate with. And it's much more faster. It can scale up to 700 gigabits per second. And obviously, knowing the power of GPUs, we wanted to ensure that we are utilizing it to the most optimal levels. We also support NVIDIA GPU Direct Storage. How many of you have heard about NVIDIA GPU Direct Storage? All right. We've got a lot of storage folks here. I love that. So for the NVIDIA GPU Direct Storage, what happens is your compute instances can basically bypass the CPU and talk directly to your GPU memory. Think about a general data path going from your storage to your CPU memory to your GPU memory. That's multiple hops that need to be managed. But what happens with GPU Direct is it allows the file system to communicate directly with your GPU memory, allowing us to give you a throughput of 3200 gigabits per second per client. So 12x higher. All right, finally, let's talk about latencies. When we built FSx for Lustre, we architected it to offer the lowest possible latencies on AWS. When I say latencies, we're talking about how long it takes for a small operation to perform. So it affects the overall responsiveness of your storage solution. A lot of workloads we work with, large compute clusters processing data, while at the same time end users or researchers are also manipulating that data interactively. And for these human-in-the-loop use cases, having fast, responsive storage really matters, because it should not feel like you're sitting for seconds or minutes just to wait for your file to open or do an operation that really matters for a researcher. Now, how do we get sub-millisecond latencies beyond just having an SSD disk for your active training data? 3 things. First of all, we allow you to, FSx for Lustre is a zonal storage offering, so you can keep your file system in the same AZ as your storage, as your compute. So that means just at a very low level, the distance that the data has to travel is really minimized. And that helps in improving latencies. Second is we do point-to-point communication, which is single network round trip. Your client server can directly talk to your file system server without multiple network hops. What you would have seen with most storage solutions is there are multiple network hops through the server, or there are load balancers. And while they're there for very good reasons, they do have an impact on the latency of the storage offering. And the third one is client-side read and write caching. So with FSx for Lustre, I like to say that we consider client as part of the file system. So anytime you read and write, if you're reading and writing, say, similar files over and over again, FSx for Lustre can cache those on your client. So in that case, you're basically having no network hops at all, and even lower latencies. So FSx for Lustre allows you to get about 0 to 1 network hops and sub-millisecond latencies. I've thrown a lot of theoretical information at you, and now I want to share how this happens, how this works in production. Shell is a great example. Shell had a GPU-based on-prem environment where they were running into infrastructure bottlenecks, so they decided to burst into cloud with FSx for Lustre and EC2. They wanted to leverage the ability to scale compute and storage up and down based on their user requirements. Now, how this helped was they were able to increase their GPU utilization from less than 90% to 100% in the cloud. So with FSx for Lustre, Shell was able to fully utilize the compute resources at full throttle. And these 10, 11-point percentage difference might not seem a lot, but those of you who are using P5 instances, this really accumulates really fast. And that concludes the file section part of the presentation. Now I want to hand over to Manish to share the options and optimizations for S3 Data Lake customers.
All right. Thanks, Aditi. Where are my Data Lake customers? Great. How many of you have heard of Express One Zone? Awesome. Few. So we'll talk about how do you reduce storage bottlenecks with cloud object storage. Many of you already have petabytes of data stored on S3 data lakes. Now, this is because you love the durability, the scalability, and the cost effectiveness. Now, this is why S3 provides you with purpose-built storage classes. Right? You're starting from S3 Standard, that's for your frequently accessed data, Glacier for your long-time archival, and Intelligent Tiering when you have changing data access patterns. Now, this makes it very easy for you to source your data directly from S3. But here's the critical point. Your storage must keep up with your compute. And as Aditi mentioned earlier, compute is your most expensive resource. And when the storage cannot keep up, you will waste money on idle CPUs or GPUs. With that said, I want you to focus your attention on one particular storage class on the left. This is Amazon S3 Express One Zone. This is our fastest cloud object storage, and it's built specifically for performance-critical applications. It will give you 10 times faster access and 80% lower request costs than S3 Standard. Now, let's look at what makes it different. First, Express One Zone is a single availability zone storage class. And we built it specifically to deliver single-digit millisecond, consistent digit millisecond access for your most frequently accessed data. Now, it instantly scales to hundreds of thousands of TPS with a new bucket type called directory buckets. Now, for the rest of the talk, we will focus on S3 Express One Zone, but some of the techniques that we talk about will apply to S3 Standard as well. All right, so before we dive into optimization techniques, let's think about a mental model that we will use. So when your client sends a request to S3, there are two parts to the request. The part on the left that's in white is called overhead or time to first byte. This is where your client sets up the connection, sets up the authentication, there's the round trip time, S3 is locating where your data is, and then serving it up. Now, no data is being transferred during this time. And then there's the second part in pink. This is where the actual data transfer happens. We're going to use this mental model for how we can evaluate your workloads. Now, there are two workloads on the screen right now. The top and bottom, they have the same overhead. This is the part in white. But notice the difference in the data payload. On the top, you will see a much smaller data payload. When your transfers look like this, your workload is latency sensitive. So think of KV caching, your shuffle charting workloads, your real-time inference serving. And this is where your overhead matters a lot more. And on the bottom, you'll see a larger data payload compared to the overhead. Now, when your transfers look like this, you care about the total transfer time or your throughput. So now that we have a mental model, let's talk about how we can optimize for different parameters, different performance parameters. Let's start with latency. Now we're going to talk about two different techniques that you can use with S3 Express One Zone. The first one is co-locating your compute instances with S3 One Zone directory buckets. When you do that, your data travels shorter distances, you have much fewer network hops, And what that lets you do is reduce the latency that you have to the storage. Now, co-locating might not always be possible. Now, in these situations, you can still take advantage of the latency optimizations, but you might pay a little bit of a penalty when you go cross AZ. So if your compute is in an adjacent AZ from your directory bucket. The second technique is session-based authentication. Now, this is a new technique that we introduced with directory buckets. Now, traditionally with S3 standard buckets, what you would use is IAM authentication. With S3 directory buckets, you would use something called session-based authentication. You would create, you would call it an API called create session. This will give you a token. Your application will cache this for a period of time and reuse that so that you don't incur a latency hit when you are authorizing with a directory bucket. Now, we understand that not every application can change overnight, so you can still start with IAM authentication and then move over to session auth when you want to optimize for latency. And whenever you're diagnosing high latency, we always ask customers to look under the hood into their libraries and make sure that session auth is enabled. Okay, so latency often goes hand in hand with transactions per second. A lot of the workloads that you run with small latency are have request-intensive operations. So think of large-scale analytics or shuffle charting. Now, with S3 general-purpose buckets, if you're familiar with how do you optimize for higher TPS, you would do that through prefix management. And the way S3 works is it scales with prefix. So it adds TPS capacity when you have constant load. Constant load, and it will basically scale up after a period of time, but it takes time. With Express One Zone, you don't need to do any of that. We handle the partitioning under the hood, and for each directory bucket, we'll give you 200K reads per second out of the box. And of course, we are continually innovating on your behalf. So this year, we added optimizations to go up to 2 million transactions per second. Now, a couple of quick tips. When you're working with directory buckets, you should try to keep your directories dense. What does that mean, right? So you should try to flatten your directory structure and keep the objects in the leaf nodes and put a lot more object in the leaf nodes. And the second tip is don't add entropy. Typically, we advise you to add entropy in your prefixes for your S3 standard buckets. Here, this will actually slow you down. All right, let me share with you how this really works in practice. Tabily is an AI infrastructure company, and they're building a web access layer for agents and large language models. They manage a two-tier caching system, and their costs were rising. They would have had to double their investment to change double their investment for their hot cache layer. Instead, they chose S3 Express One Zone because it delivered the low latency and the cost efficiency they were looking for. This is for their hot cache layer. In addition, it just scaled automatically as their data grew. You can see the results. They were able to cut costs by 6 times while improving performance and reliability across millions of user requests. So this is latency and transactions per second in play. Now let's talk about high throughput. Now many of you are running workloads like large-scale ML training or research workloads. This is where data loading and checkpointing becomes important. You need massive throughput so that you keep your compute fully utilized. So one of the techniques we're going to talk about is parallelization. Now, since S3 scales horizontally, the way to increase throughput is by breaking up your requests across multiple connections. In this example over here, you can see that each connection can achieve 100 megabytes per second. Now, if you need gigabytes per second or terabytes per second, you open up multiple connections. So how do you accomplish this with APIs? Right? So when you're downloading, use byte range gets. This is where you will download parts of the object, and then you'll have to assemble that on your compute node. If you want to upload, you use a similar technique called multi-part uploads, where you would upload individual parts, and S3 will assemble that for you. All right, so I'm very excited about this example. This was mentioned by Andy in the keynote yesterday as well. Meta Fair is a research organization that runs research workloads, including LLM training, across thousands of GPUs. They wanted to speed up their checkpointing and data loading. And what they did was they used S3 Express One Zone. We scaled up an AZ with 60 petabytes of data in one AZ where their GPU clusters were located. And they were able to sustain 140 terabits per second with over 1 million transactions per second. Isn't that neat? Okay, so let's talk about the client-side optimizations. We saw that some customers were not able to fully utilize the compute resources using the techniques that we just discussed. So we built the AWS Common Runtime, or CRT. Anybody heard of CRT over here? Oh, not many people. This is great. So let's talk about it, right? So it's a set of open source libraries. And what we did was we embedded these libraries right into all our SDKs, all our clients, all our connectors. So you get performance improvements with S3 right out of the box. The great thing is you don't have to change much. An example here is that CRT will deliver up to 6 times faster data transfer with CLI using some of the techniques that we just discussed, right? Just keep in mind that for P and TRN, the larger instances, we enable the CRT by default. However, if you're using some other instances, please look under the hood. You might have to enable this and opt into CRT so that you can take advantage of some of these techniques. So similar to how Aditi spoke about multiple NICs and how you can increase the per instance throughput, we have a similar feature in AWS CRT. So instances such as P5 and P6 can achieve 800 gigabits per second theoretical bandwidth over their ENA network interfaces, right? So this CRT feature allows you to distribute your connections, your S3 connections, over all of these network interfaces. Now, this is particularly important if you're using EFA for your for your compute-intensive workloads. It prevents EFA slowdowns, and your compute and storage traffic can both run optimally if you spread the load. How do you do that? It's as simple as just setting the config and picking the network interfaces that you need using CRT. Let's look at some sample results. So we ran tests on a DL24XL instance. We downloaded 10 30-gigabyte files. When we added a second NIC, we were able to almost double the performance. We could get almost double the throughput. With 4 NICs, we were able to get about 2.5 times the performance compared to a single NIC. Now, the scaling doesn't look linear, but you will get some meaningful throughput gains when you add multiple NICs. But the more important thing is that you can spread your traffic or even pin a particular NIC to your process. So this will help you optimize how you control. This will help you optimize your workloads when you're using a much larger instance. Okay, let's talk a little bit about integrations, right? So these were all libraries that we spoke about, but we heard from customers that they didn't want to change their application, and they wanted to take these best practices and use them with the existing frameworks that they had. This is why we developed purpose-built integrations so that you could take performance off S3. We're going to only talk about 3 of them, but we have a lot more integrations that we have developed. So the first one is the PyTorch connector. Now, when you use PyTorch, you have to build your own data primitives to load and save data when you want to load the data or you want to run checkpoints. So we wanted to give you a high-performance integration that took care of a lot of this. This is where the S3 connector for PyTorch comes in. Now, this gives you built-in PyTorch dataset primitives, and it supports both map-style datasets. This is for your random access data, and iterable-style datasets, which is when you're streaming sequential data. Now, for checkpointing, the connector automatically integrates with the PyTorch distributed checkpointing support. With this, you can checkpoint directly into S3 Express 1 zone, and you can bypass the local NVMe. What we found was that you could get up to 40% performance increase by bypassing the local storage and going directly to S3 Express 1 zone. New for 2025, we've accelerated partial checkpoint loading by 60%. So this is another example of how we're innovating on your behalf. How many people here work with Parquet data sets? Awesome, quite a few. So you probably already know that your query engine has to read metadata from Parquet files, and this metadata is stored at the footer of these Parquet files. This metadata stores information about the file structure and what the schema is. So when you're scanning across multiple of these files, what you will see is that the metadata will slow down your query execution. So this is where the S3 Analytics Accelerator comes in. This is an open source library. It prefetches metadata using byte range gets. It reads the footer. And it also caches this footer for subsequent reads. So this eliminates quite a bit of overhead. We tested this with TPC-DS. This is a benchmark that you can run. And we saw that we were able to achieve up to 27% performance improvement just by using the Analytics Accelerator. Another integration I want to talk about is SageMaker. If you're not familiar with Amazon SageMaker, it's our fully managed service. And it's built for building, training, and deploying machine learning models. Now, when you're running training jobs, you need to load your training data, often millions of, if not lots of small files, like images or text samples. And this will generate millions of requests per second into storage. Now, this is where our S3 Express 1 zone integration with SageMaker Fast File mode comes in. Now, what Fast File mode will do is it will stream data directly from Express 1 zone into your training instance, bypass the local disk, and accelerate your training performance. Now, since Express 1 zone scales to hundreds of thousands of TPS, you should be able to see meaningful performance increases with this approach. Great. So earlier, Aditi covered how you can optimize interfaces for high-performance file interfaces for high-performance workloads. We went through some optimizations for object storage. But what if you already have a lot of data in your object store, and you want to use a file interface to access that? So this is where Aditi will show you how you can bridge the two.
Thanks, Manish. All right. I'm only going to speak for 5 more minutes, and this is the favorite part of my presentation, so listen up. So I shared a lot about high-performance file systems, Lustre file systems, fully managed, fully elastic, in the beginning of my presentation. And if any of that resonated with you, or you felt, oh, but my data is already stored in S3 Data Lake, then don't worry, we got you. We basically have the option to connect your file system with your S3 bucket. This is also just a general paradigm we use within AWS that we want to meet where you're at, and we want to minimize the work that you have to do to move to the cloud or run your applications in the cloud. Let me show you how this works. So with FSx for Lustre, you can create a file system and link it to the S3 bucket. Under the covers, this is your S3 bucket. It has all the objects, all the data stored in it. When you connect your file system to the S3 bucket and try to read and write data from your compute instance, what it does is it immediately takes all your metadata from your S3 bucket and shows it as file metadata on the file system. So for you, it would seem like the data is actually on the file system. When you try to read and write data onto the file system, FSx for Lustre will automatically go and fetch that data from S3. Now, another interesting fact here is that we take care of bidirectional synchronization. So any changes you're making to the file system, we are exporting those changes to the S3 bucket. And any changes you make to the S3 bucket, we import those changes to the file system. completely hands-off for you and fully managed on the back end. You can think of this as a file system cache in front of your S3 bucket. Let's look at a performance when a file system is in front of S3. We took a Kaggle-delivered dataset stored as a public S3 dataset and measured the time to do patient classification with different setups. So the first one that you see right there is where you have your data stored in S3. You load it to your local storage, and then you train against that local storage. What we did was we tried to do a test where we used FSX for Lustre as a cache between your compute instance and your S3 bucket. In the first run of that model, we saw a 67% increase in performance. Now, that increase in performance was coming from two things. The first one, you see that green color over there? That is the data loading time, where your compute instance is copying the data, and it has to copy the data, wait for it to be completely loaded before it can start training. With FSX for Lustre, you spin up your instance, and you start training immediately. So we save on the data loading time. And second is just pure performance that a fast file system delivers, which leads to this cumulative impact of 67%. Now, this was the first run, where FSX for Lustre was still going to S3 to get that data for you. In the second run onwards, you would see that the performance is improved by 83%, and that's because the data is already cached onto the file system. So finally, one last customer example to bring all of this together for you, LG AI Research. This AI research lab within LG wanted to create a foundational model that mimics human brain. So they decided to build their own model using Amazon SageMaker and FSX for Lustre. On the left, you see that they store machine learning training data in their S3 bucket. And for performance and a file interface, they created a Lustre file system linked to that S3 bucket, and their SageMaker training jobs was directly accessing their data through the file system. When workloads finish, model artifacts get written back to S3 for long-term storage and for inference. So they use S3 for longer-term storage, FSX for Lustre for their highest performing hot data to accelerate their training runtimes and getting the best performance out of their instances. This concludes the presentation we had. We basically tried to cover high-performance storage options depending upon whether you're looking to lift and shift from on-premises or you prefer a file system interface, which is FSX for Lustre, or if you have an S3 native application where you can use S3 Express one zone. And then if you prefer file system interface, but your data is stored in S3, then you can basically mount your file system to the S3 bucket. Thank you all for attending. If you haven't already, please complete the survey. You should get a notification in your app. Manish, Mark, and I will stick around to answer any questions you have on anything related to high-performance storage.
Right.
Thank you.